So,
Yes.
good one. I like that. So, I'm Andres. I do math because it's fun. Because I don't need a reason. And it turns out that this this desire to have fun has led to jobs that pay you the bills to have more fun, which is great. And yet, I just want to make sure that you understand that my main motivation is not necessarily that. My motivation is the fun. The profit comes as an after effect. So, please parse the title like this: for fun and profit, which is important. So why the fun? I don't know why. And it took me quite a while to realize that what I really liked was math, not just programming a computer. And I have a special fondness for integers. And what? No, we did not. Proof. So, I don't have anything for you to read. So, I need you to pay attention to me. I'm talking. So, you know. Do you want to come here and give me a presentation? Okay, knock it off. So, with all due respect, but okay. So, this fondness of integers comes because of random accidents, like a computer teacher when I was a kid telling me, "Oh, you won't understand assembler. You're too young for that. I'm not going to teach you." "Oh, you're not going to teach me." Okay. So by age 13, because see, at that point I assumed, okay, nobody's going to tell me anything, so I'm going to have to figure it out on my own. And I wasn't finding, for whatever reason, good material. So by age 13, I realized that there was this modular arithmetic thing where if you wanted to subtract, say, here you have a range of your integers, say from 0 to 255, and you subtract 30 from 250, you get 220, and that works. But if you have 30 and you subtract 220, then it doesn't work. So, well, these negative numbers are not there, and I realized after thinking a whole bunch that, oh, right, I can just plug them back in here, and then, oh, right, it works, great. And all of this because I wanted to do compression, and all I had to go about this was some random text that said, oh, and byte, and what those numbers were. So, by accident, and not in the most efficient means, that led me to have a rather visceral appreciation, or very direct, intellectually almost violent appreciation of integers. Because, it's not something it's not all something that I read. And the shock you get when you get to understand one of these on your own is extremely strong. And you remember that. I know you like it. And you can stop it. And so, integers. What to do with integers? Well, you can imagine all sorts of things. We can compress data. You can find very efficient ways to calculate things. Let's try factoring integers like crazy. Let's learn assembler too, on the way, because why not? And that led to trying to compress data. And while compressing data, I realized, well, I'm going to need some visualization tools. So let's write them in assembly. Because why not? This is the output of some of my first assembly programs. And what you're looking at is a histogram of values for some audio. And here you can see a red dot that's marking the average value, which will be interesting in some other thing that I'll show you in a moment. And what you can see here is that this is PCM, right? So in PCM, it's choose complements notation. So basically, well, not exactly, more like one's complement. Well, whatever. So basically, 0 is, well, the 0 of the wave is at the center of the wave function, right? And higher values represent things going up, and 0 represents all the way to the bottom. So this is telling you is that, hey, most values are rather small. This is plotting differences between pairs. So there's a lot of pairs of values that have 0 as a difference, and then less, and then -1, right? So very nice. What else can we look at? We can look at, this is a histogram of number of times a certain byte appears, And we can see here that, well, that's not compressed very well, right? Because why? Well, value 0 appears a lot. That's not good. And look at this. Supposedly this is compressed, right? But now you start seeing this combing effect, right? Because this is, well, 128 appears a lot, and here's like 96, 64, etc. And you can recognize all the interesting numbers that you can find between 0 and 255, like, 192 and so on. Okay, well, let's look at this. This is bytes that appear in 1.4 gigabytes worth of XC-9. So that's LCMA racked up to as much as it can do. And yet, look at the combing again, right? Look at this. What's that all about? Now, this is fun. This was fun for me. But it's also fun to make it work. And to show you, I have prepared this thing where I have a few files in here. So let's see. So, oh, come on. There we go. Right? So here you can see pairs, right? I mean, it finishes very quickly because the file's small. Sorry about this, but whatever. So, and here you have a longer audio, and you can see the values changing a little bit, right? So look, very small deltas, right? Now let's take a look at the actual values that appear in there. Right? These are the values that appear. Right? So, and something interesting to do with that is to try that with those, let's try that with MPEG file. Right? See, that's a lot of 0. And what happened there is that a lot of 0 was at the beginning, and yet there's enough zeros as the file goes by that the other values never recover. And you can verify that by looking at it. And if you look at the XZ, you can see something very strange. So that's 1.4 bits of XZ. But look at that. It goes down, you see it coming up, and then the data changes a little bit, right? And it starts getting up again, right? So if you look at this and you think hard enough, you're going to think, that coding is not as efficient as it could be. I don't know how it could be improved, but I can tell you, look, if you run a arithmetic coder on this thing, and if you know these probabilities, you can make the file smaller again. So that's a lot of fun. The next incarnation of that is this. The function plotters I wrote a while ago. And these I wrote to teach myself more about visualization and look at histograms and all sorts of things. This is one of the original shortcuts screenshots I wrote, where I took with my Asian computer. It says, the function is the quantity of primes in the factorization of x floor is in polars, where 0 is 0, so that's 0 there, and 256 is 2 pi, this guy. One turn in polar coordinates, a new plotting mode, alpha filling to the origin. That's why it's plotted this way. So you can see this is a lot of fun, right? So that also led to, well, compression, and that leads to writing a lossless ADPCM codec, presenting it in a paper, and putting that out. And this is very nice, because all this junk, what it can do is compress better than LC plus Huffman with about 40 bytes of storage. So it's very nice, right? And it's also lossless as opposed to many other ADPCM codecs. So this gives you an appreciation not just for compression of data, right? But also for compression of understanding. You don't want any extra details anymore. And the more you do it, the harder you can move this handle so these things meet. And now you're thinking about less stuff, and because you squish it like this, it has less distracting stuff. And now you're thinking more clearly, and now things can happen because you're not wasting your time on nonsense. Moreover, there's also the strict sense of, hey, let's actually prove this works, because once you understand that math is a nice tool, then you want to pick up the math and throw it at the program too. So what happens when you apply this in real life? Well, I had a chance to use that Vise, this Vise squishing technique on a lot of other things. And I thought of these 4 examples that I think illustrate that very well. So let's say you take some piece of code and you change it somehow, right? So we're going to see what happens first when the change code has basically the same speed and the same size. This is a fabulous example I found not long ago. What does this instruction do? And if you figure it out, don't say anything. You know x86 assembly? So, if you don't, I'll wait a little bit and they'll tell you. Alright? Okay. So, what this instruction is doing, right, is LEA is load effective address. So basically calculate the address pointed to by this pointer and put it into that register. Every person I've asked, what does this instruction do, gets stuck, because it's very confusing. When I found it, I got stuck, because it's also very confusing. Wait a minute. So, get me the address that is pointed to by the ESP register. Oh, you mean the ESP register itself, right? So this is not LEA. This is move EDX ESP, right, without the square brackets. And all of a sudden, it's much less confusing, right, because you realize, oh, that's what's going on. So, this kind of intellectual noise or back chatter, you don't want in your program. Right? Make it go away. And this is how math now helps you, because now you can prove, if you know just the most rudimentary tools of Algebra 1 and Calculus 1 or whatever, you can prove that, oh, if I replace that with move EDX ESP, it's the same thing. And you actually can go and actually have an argument with yourself trying to convince yourself that, indeed, rigorously, it is the same. If you learn to do that quickly, now you can do a lot of cleanup like this. And so for comparison purposes, Dr. Hatch down there and I took about 7 years to take out 35% of the VisualWorks virtual machine in terms of source code. After that training, I went to my lovely new job, and in about 2-3 months, again, that happened, the same 35%. So it's really useful, right? That's nice. Because now look, I don't need to deal with this anymore. What other things can happen? Well, you can write something that is the same speed, but is shorter. Usually this is called refactoring. Whatever. It's called refactoring. And I have a wonderful example of object relational mapping framework that I had to deal with, because it was very verbose. It was terrible. It was super verbose. It had bugs. It didn't have debugging tools. It didn't have validation tools, and it produced a ton of code. And on top of that, the mapping that application was doing to the database had about 112 errors, and the thing just appeared to work. When I was done with it, so it has tests, it validates itself, it has no errors, and it has 1/10 of the source code, right? Oh, right, I can deal with that, right? Let's take 360K, no. Slash it by 10 and end up with 36K. That actually, work. And you can do that if you have math, because now you can prove it, right? That this actually, has to work. Not just, oh, I like it, or it appears, or it satisfies my subjective artistic feelings. No. It actually works, right? And that's nice, because now you enable your new success with this. You can take the same size and make faster. This is usually called optimization. And we have a wonderful example with hashing. So it was at the bank that I was working on. And one day some users come over and say, hey, we have this report that is running after all the calculations are run. It takes half an hour, and for half an hour we can't leave. And there's nothing for us to do other than go like this and wait until they can go home. Now, these are people that work extremely long hours. Very long days, holidays, weekends, etc. Half an hour is a big deal, right? So I put that in the profiler. Turns out that all the time is being spent in linear searching hashing in a dictionary. So it's like, well, no. So I look at the hash method, and it's in my book, whatever. I've spoken about the particulars of it a number of times. But basically, I ended up replacing a hash function that was very quick with one that was 5 times slower. You wonder what the heck? Yes, 5 times slower hash function, but those 30 minutes went down to 90 seconds, and hashing was gone from the profiler, right? Because the other hash function was creating so many collisions that it was, hashing was degenerating to linear search. No algebra 1, no calculus 1, you missed that. And it's also very fun, right, to see the time go like this, and there's nothing to do anymore. It's rather pleasing, and it's rather nice. And then, of course, you can make faster and shorter. That's the awesome category. And I did something like that with an object table compactor. So the original object table compactor that I had to deal with was about 1,000 lines of code in total. And yeah, the object table and data compactor. It was about 1,000 lines of code. The main section was full of macros to save code, unquote. And because the macros were called in a spaghetti fashion, you couldn't follow the code. Plus the code was buggy and slow, and it had quadratic complexity at times. So you put that in the Vise, and this is what happens. So first off, the code drops in half. You can actually find a proof that the thing has to work, and it does. And you can test it too. And you also remove all the quadratic complexities out of the way, and your whole test suite runs 20% faster. That's a whole lot of things, not just garbage collection. So as you can see, for problems that have a clear solution, having this experience with math and actually liking it has the side effect that you can actually now enjoy the work you do. And the results are very nice. So people like it, they pay your bills, and you get to do more. Now that's for problems that, they have a solution. You can imagine, number theory, blah, whatever, by induction, yeah, sure. What happens with problems that don't have easy solutions? Right? What happens when the solution is not obvious? Math helps there too. And for that, I need to go back to this, the 2006 coding contest. Yes, that's right. So, in the 2006 coding contest, I was a participant, and in the original phase, basically you're given a problem, you have some time to make a solution that appears to work. And if you pass the test, then you go to a final in which you're given a modified program. You are not told what the changes are, and in 2 hours you have to fix your program, and it has to work, and then you compete. You see which one wins, right? So, to deal with this, basically you have to make a program that plays several varieties of Pong. This is one of them, the easy one. But there's others, like multiple bats. They move like this, or in parallel, or whatever, or multiple balls, and so on. So, in order to deal with this, I did not just write a piece of code that solved this problem. I wrote a framework about how to play any game. So that's raising the level of abstraction way, 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 way up. And I did that because then I knew that I could make a simple application of this framework, and the framework would continue to work, and I wouldn't have to deal with the framework when people would make changes to things. I would just concentrate on the game. And yet, the really interesting part about this was the pattern that came out of it. This thing, without knowing anything, I ended up calling the perception pattern. And it's a pattern of organization of objects that is suited towards, this could be anything, but in that case, look, get stuff from the HTTP server that tells you what the game is doing. Well, that's ASCII. That's not very helpful. Okay, fine. So, make a parser that turns ASCII into objects, right? That's the work of the eyes. The interface doesn't do it. So the eyes look at stuff and say, oh, you mean, you have a ball, you have a bat, and the ball is moving like this, okay, fine. Now you perceived, and then processing goes to some other stage, goes to the strategy. The strategy looks at what's going on, not in terms of ASCII, but ball, movement, blah, vectors, whatever, and says, very interesting, I want to do this. But you don't choose the command. Actually, you get a function you want to maximize, so you express an objective as a function that you want to maximize. You don't maximize it there. You put that, you give that to the hands. The hands look at the function and say, oh, very nice, if I want to maximize this, then given the state of the world as of my last iteration, this is the command I would have to choose to like move the bat or do whatever. Tell the interface to send the command, because of course these objects don't know anything about the HTTP interface, they should not, and the interface sends that to the HTTP player, and off you go. Oh, okay. And you can actually write informal proofs that say that this actually has to work. And if you write it nice, you can actually afford huge mistakes in those 63 hours, or huge like blunders. Like for instance, the first thing I wanted to do was that each of these would be its own process, right? But I found that every time the interface talked to HTTP, the HTTP server would delay the response. And so it would make everything stuck, right? And I only had to change one method to make it go from 5 processes to 1 Smalltalk process. In one method. Because of the Vise, right? Because of wanting to squish everything down. That's very nice. And I ended up reusing it in the 2007 coding contest. Because, yes, sure, I got an iPod because I won. And my other prize was, here, Anders, go organize a new one, because why not? So that was my task. So in the 2007 coding contest, I took that experience that I had about problems that have a different solution, and I decided, well, I need to give these people that are going to participate a problem for which the solution is not obvious. Because what if I give them a problem for which the solution is obvious? Well, they're going to Google the problem, implement algorithm such and such without thinking, there they won, right? Well, that's not fun. So no, let's make something so that the solution is difficult to find. I thought about this game. Everybody knows the memory game, right? So you have a whole bunch of cards, and they're facing down, right? And your task is to pick one, say this one, and now you have to find where is the other one, and every time you uncover 2 that are a pair, you can remove them, and when you're done removing all the cards, you win. Well, that's a stupid game to play in a computer, but it can be modified. The key that makes the computer an obvious tool to solve these kind of problems is the computer knows the positions of the cards. Let's hide the positions from the cards. And instead, let's introduce this pseudo-computer. Right? So this pseudo-computer has a bunch of registers and memory slots. These are the registers A, B, and X, and the memory slots are here. So what the computer can do is run instructions. Right? So one of the instructions for registers A and B is fetch. That fetch instruction hides the position from the computer, because now all the computer sees is the little stars. The game takes care of actually, like for instance, having a scanning pointer that goes like this, and each time it gives the computer a different card that it doesn't have, so the computer can by accident flip up the same card, right? And all these things. You hide that away. And now all this poor computer sees is a string of things, right? So when you do that, you make it say, let's say we're playing the game, right? So we fetch on A, and B is empty, so we can't match anything, right? So okay, so we could fetch on B, and now we have 2 things in here. Let's say they're different, because if they're the same, it's kind of easy. So now only registers A and B can solve a pair, right? And so, well, what to do? Well, put one of the things in X, and now you can fetch again. And if you still don't have a pair, then well, now you need to spill X into memory, and you get the idea. And so what happens is now the poor people playing have to implement effectively cache management algorithms. And because they don't exactly know what's coming, the solution is not obvious. That's what's interesting about this, right? And again, the perception pattern is behind it. And this is also about math. It's about optimizing problems, right? 2008 coding contest, I also wrote this. And in this case, I modeled a work environment team. This is a development environment team, and this is your poor computer program that has to play the game, and this computer program has to play and try to be nice while working on a software project with, say, Dilbert, Alice, Ashok, Dogbert, Ratbert, and Wally. Each of them with their own personality, right? This is awesome to program this, because now you get to see, as Leandro was saying, in the simulation, all these social dynamics that you're so familiar with. You see them playing again for yourself. Like, for instance, get a team of Alices, right? Very productive, doesn't tolerate stress. Just a little bit of stress that gets into the system. Boom! All the people irritated at each other, emails, spam wars. It's fascinating. We've all seen this, right? But then you get to see it like this. The star of the show, though, besides the fact that all these things were implemented with the perception pattern, again, was this, the arctangent. You wonder, what the heck? What do you mean the arctangent? Well, yes, because if you're going to model things like irritation of someone, you can do this. You take the arctangent and you say, like, you start your day and everything's so nice, and you start getting irritated, and each time you get irritated, the irritation point moves to the right. And it moves to the right in proportion to the derivative of the arctangent at that point. So at first, oh yes, I'm having such a nice day. Oh, I got awful emails from whoever. Okay, well, I don't care. And then I spilled coffee on myself. Oh, okay, fine, whatever. I'm doing lunch. Someone was rude to me. And then, I had problems with food, and the bathroom was terrible, and all these awful things happened. And by this time, you're not listening anymore, right? Not only that, right? Actually, it goes like this, right? It doesn't go linear, so it goes like this, and now you're over there. And once you're over there, it's going to take you a lot of relaxing to go back, right? Because, oh my God, I'm going to listen to nice music. Oh, I'm going to take a nap. Oh, fine. Oh, I had a nice day, right? Now, you can do that with people. You can do that with how much a work unit is finished. You can do that with the probability that there's going to be a bug in whatever thing was being worked on. You can do all these things just with the arctangent. And other people have found the arctangent tries to actually model bipolar behavior, but I found that later. So, what does this have anything to do? Because this is super fun, right? What does it have to do with real problems? Well, suppose you are given charge or given control over a computer cluster, right? And you're told, hey, actually, make it run efficiently. Well, you can do that by hand, but only in the times you're at the office. What if you're not at the office? What if you're sleeping? Because, remember, you also have to sleep, right? Well, I'll tell you what. Let's make the thing self-aware and throw one of these perception pattern at it. Right? Oh, you mean, this thing goes, let's take a look at what's going on in the cluster. Oh, I see that machines are busy with these jobs and the other. Oh, I have strategy. Okay, pass that to the strategy. The strategy says they minimize running time. All these things are running all wrong. Hey, minimize running time, please, by, prioritize this, prioritize that. I don't care what you do, but just do it. Okay, fine. Shut down this place, whatever, and start these jobs here, over there. Okay, actually do it, done. And you give it rules, and you give it a nice scheduler. Done. You never deal with that again. But this is a real-life project now. You see? All because you like math. How about this other one? Oh, here. I have to deal with a memory manager system for random programs, and I have to minimize running time of applications over which I have no control whatsoever, right? Because, should I grow memory? Should I garbage collect? Should I grow memory like this? How aggressive should I grow memory? Should I run the incremental garbage collector or not? What do I do? Right? Well, what you throw at that is the experience you get from dealing with this. And all of a sudden, something that didn't even finish because it crashed in over a day runs in 73 minutes. That's why. And this is nice now, right? Because you get to take your fun and do it again and have it actually be useful for people and reliable, because you picked up the math, monkey wrench, and you bash the thing into compliance until you actually prove that it works, right? I don't care. You're going to be reliable. Bang! I said, right? And you get to do that because you did all these exercises, squishing the code into nothing. And removing all the intellectual dirt from your mind, because otherwise you can't think, right? So, in short, I like math. I like it a lot. I like integers a lot. Not only because it's fun for me, but also it's because it's very rewarding to use them in real-life situations. You only get to have that fun in your real-life situations if you actually develop an appreciation for it. It's not very hard. It just takes losing hair and, bunch of times no sleeping and whatnot, stressing over the book that you don't understand. But I assure you, after much work, you can do it. I could do it, you can do it. Right? Bach said it better. Anybody that does as much work as I did will get the same results. Well, I think that's true. So if we could actually do it, I think it would be so much nicer. Because imagine, it's so much nicer. You deal with smaller programs, things that work, things that don't crash, things that run faster, don't make me wait, right? It's nice. Not only for problems in which you know the solution, like we saw, but also for problems in which you don't even know what the optimal solution is. Because you can even go ahead and express an algorithm that searches that solution for you. Thank you. And if there's no time for questions, there's no time for questions.
Because we're running late. So let's try to make a 15-minute break. Okay?
So Andre.
Yes, my little friend.
Finishing with the mathematical branch.